Polynomial functions are smooth and continuous. This function here, this is an absolute value transformed function. This is not a smooth function. Now, in fact, it meets at a point here, and this is exactly what makes it not smooth. This point is called a cusp. That makes this thing not smooth. There's other reasons for why this is not smooth, other more specific reasons, but you have to get into calculus to understand that. This next function is not continuous. A basic idea of continuity is if you were to draw the function, you needed to put the pen down on the page and draw it, and then at this point here, we'd eventually have to pick up the pen off the page and then go up here and draw it with another line. This function here is all within one stroke of a pen, so there's no need to pick the pen off the page. That means it's continuous. So this is a non-continuous, but not continuous function. This one here is smooth. It has only these smooth curves on it. There's no jagged points or jagged edges. And I can draw it all in one go. So this is a polynomial function. The domain of all polynomial functions is negative infinity to infinity. There's never been any issue with plugging numbers into them, as we've seen in the previous videos. So the domain is always going to be everything whenever you're working with a polynomial. The end behavior, of course, can be looked at looking at the leading term, as I've shown in the previous video. Really, the leading term dictates most of the behavior. So if you look at the leading term and then compare it to either x squared, x cubed, negative x squared, or negative x cubed. Okay, let's look at some polynomial functions and just kind of identify some behavior of them. This first one is a quadratic. That's the leading term right there. And the leading coefficient is positive. So you can see it goes up to the left and up to the right. You'll also notice that this one has just a single turning point. Of course, this is at the vertex, we know. So it has a single turning point. That's, of course, called the vertex for a quadratic. And that means that it has a minimum. This one, with all these conditions, has a one minimum. You'll also know that this thing has two x-intercepts. Okay, for this next one, we have a4 x to the fourth. That's the leading term. A4 is greater than 0. So again, we have up to the left and up to the right, just like we would for x squared. And you can see, well, this one actually has 3 turning points. Of course, these turning points, there's 2 minimums and 1 maximum, but there's 3 turning points in total. There's also 1, 2, 3 x-intercepts. Okay, this one is a6 x to the 6, but here we have a6 is less than 0. The previous ones have been greater than 0. This one's less than 0, and that means that it's going to go down and down to the left and to the right, as opposed to up and up as the previous two did. So this one has, let's see, 1, 2, 3, 4, 5 turning points. That means it's got what, 1, 2, 3 maximums, 1, 2 minimums. This one here, I should say, this is a global maximum. These two are local maximums. And these two are only local minimums because the function continues downward indefinitely. So they're not global minimums. This is a global minimum here for the quadratic. This is a global minimum, local minimum, and this would be a local maximum because the function continues upward indefinitely. This one has, let's see, 1, 2, 3, 4, 5 x-intercepts. And maybe you can see some types of pattern here between the different polynomials. Let's just keep looking at some more. These one down here, these are all odd powers. So this is x cubed, x to the fifth, and x to the seventh. A3 is greater than 0, so we know it's going to follow the regular positive x cubed, down to the left, up to the right. It's got 2 turning points. One's a maximum, one's a minimum. And we can see that it has 1, 2, 3 x-intercepts. Okay, the next one, again, a is greater than 0, is an odd power, so it's going to go down to the left, up to the right, just like the regular positive x cubed does. It's got, let's see, this one has 1, 2 turning points. This is not actually a turning point. This is technically called a saddle point because of how it looks. It actually just flatlines for a single moment. It becomes 0 just right there for a single moment, and then it continues upwards. So it's increasing, then decreasing, and then at this point it starts increasing again. So it's increasing, increasing, increasing. It flattens out for just a moment, and then it continues increasing. So that's not a maximum or a minimum. So I got 2 turning points. And it has 1, 2, 3 x-intercepts. The final one is a7 is less than 0. So we know it's going to follow the negative x cubed. That's up to the left and down to the right in behavior. This one has, let's see, 1, 2, 3, 4, 5, 6 turning points. And it has 1, 2, 3, 4, 5, 6, 7 x-intercepts. Now, looking at all this stuff, it may not be apparent at all what the pattern is that I'm trying to show here. But I was looking at the turning points and the x-intercepts specifically. These have a lot of, all polynomials have these kinds of behavior that you want to kind of look at. And looking at these things, we can actually say it always has up to n x-intercepts called zeros. They're going to be called zeros because at these x-intercepts, y equals 0. Same thing is true for all of these. Y equals 0, y equals 0, y equals 0. And of course, this one has 7 of them. So all of these things have y equal to 0. That's the same thing as saying the function f of x equals 0 at each one of these spots. So saying the function has a 0 there means the function equals 0 at these points. It's the same thing as an x-intercept, but it's just a different word to point out the fact that it's not where it crosses the x-axis, it's where the function is 0. That's the idea we're trying to get across with that name. And then all of these have n minus 1, or I should say up to n minus 1 turning points. And these are all the extrema, or the maxima or minima. So has 1 minimum, 2 x-intercepts. This is a n equals 2 here, right? It has equal to the number of x-intercepts, and then n minus 1. So 2 minus 1 is 1 turning point here. This one has n equal to 4. It has 3 x-intercepts. It could have 4, but this one only has 3. It does, however, have 3 turning points, which is the maximum it could have. This one, n equals 6, has 5 turning points. That's the maximum it can have there. It can have 1 more x-intercept. The reason why it doesn't is because both of these, this one and this one, don't have the maximum x-intercepts, because at this point it just touches the x-intercept and it turns around there. The same thing happens with this one. It just touches it and turns around. If it were to cross it, however, or do something like this, then you can see it would actually have 2 more, or an additional 1, I should say. and that would make it to the maximum for each of these. And of course, the same thing happens for these. This one's cube. It has the most turning points it can have. 3 minus 1 is 2. And then it has the most zeros it can have. So the same zero as the degree. And so on and so forth. That's the kind of analysis I want you to think about when you're looking at polynomial functions. Okay, so what's the end behavior, the max number of zeros, and the most turning points of the following functions? So end behavior is always dictated by the leading term. The leading term is this one. It's got a negative coefficient, and it's got an odd power. So it's going to look the same as negative x cubed. If you don't remember what that looks like, just graph it, and you're going to see that you're going to get, as x goes to negative infinity to the left, the function goes upward. As x goes to the right, the function goes downward. Okay, that's the end behavior. The maximum number of zeros, well, that is the same thing as the degree. So max number of zeros is 19. And the most turning points, so max number of turning points is n minus 1, so 18. Of course, go ahead and graph this function out and see what it looks like, and you're going to see that it's going to fit this description. Okay, with the next one, again, the leading term. This is the leading term, not this one. Even though this is a very large number here, that doesn't matter. What matters is the leading term. Leading term here is positive. It's an odd power, so it's going to follow the positive x cubed. Looking at that function gives us, as x goes to the left, the function h of x goes downward. As x goes to the right, the function goes upward. Okay. The zeros, the max number of zeros is 15, the same as the degree, which is n, which is 15, I should say. And then the maximum number of turning points is n minus 1, so 14. Give it a try in number 2. Now, because the zeros are x-intercepts, which have the y equal to 0, we can find them algebraically. This is going to be an important part of working with polynomial functions, or functions in general, really. If we count multiplicity, the number of zeros will always add up to the degree. Multiplicity is the idea that a polynomial has zeros at the same location multiple times. And if you count all the multiplicity up, you'll always equal the degree, whatever the degree is for the polynomial. Now, at these zeros, the graph behaves differently depending upon the multiplicity. So not only does the multiplicity let you add up multiple zeros to get to the degree, it also tells you how the graph acts at that x-intercept, or that 0. If it's an even multiplicity, then the graph will turn around, or it's a turning point at that 0. If it's an odd multiplicity, the graph will cross that x-axis at that point in some fashion. Okay, we're going to find the zeros of these things without graphing, and then we're going to sketch a graph of these, very basic, and then we're going to look at a graph. So first off, we have a cubic, right? This is the leading term, so it's going to follow, of course, positive x cubed, the monomial function. So we know the end behavior is going to go down to the left and up to the right. We also know that this thing has, since n equals 3, it has up to 3 x-intercepts. It also has up to 2 turning points. We can actually look at this thing and ask, what are the zeros? The zeros are happening when this thing equals 0, and then we're going to factor it. This I can factor by grouping. I can take out an x squared from the first two terms, take out a -4 from the second two. That gives me x squared minus 4, x plus 7. And then I can factor this. This is a difference of two squares. So we get x minus 2, x plus 2, and then x plus 7. Okay, with that, we know it has zeros at, so x equals 2, -2, and -7. So it has the most zeros it can have. There's 3 zeros there. And each one has a multiplicity of 1. When you factor it, the power on there is the multiplicity. And each one of these has a multiplicity 1. So we know it's going to cross the x-axis at each one of these. So to give a very quick sketch of this graph, we know that's going to go up to the right, down to the left. It's going to cross the x-axis at, let's see, 1, 2, 3, 4, 5, 6, -7, and 1, 2. So we have this behavior here. It's going to look, polynomial functions are smooth and continuous, so we're going to draw a smooth curve through all 3 of these points following the in behavior. It's also going to have up to 2 turning points, so make sure it doesn't have any more than that. So it's going to go down here. I'm going to draw like this. I'm going to draw like this, and then go down, and then up like that. So that's just a sketch. I haven't calculated any other points. I've just gotten a basic idea of what the function may look like. If I want an exact idea, I'll just use graphing software. You can see it has 2 turning points right here and right here, 1 max, 1 minimum, and it passes through each one of these zeros once. Okay. The next one here, this one's already factored. This one is a, let's see, there's 2 from this one, 3 from this one, 1 from there. This is an x to the 6th power. If you were to expand it, you're going to see that the leading term is going to be 7x to the 6th. So that means we know it follows the positive x squared end behavior. So up to the left and up to the right. Okay, now with this one, we have 3 zeros, only 3 zeros. We have 2, -3, and 4. Of course, this one equal to 0. Get a 0 from this one at 4, this one at -3, and this one at 2. And you can see that we have multiplicities that are different on each one of these things. So this one has a multiplicity of 2. This one has a multiplicity of 3. And this one has the multiplicity of 1. Because the power here is 2, this one's on 3, and this one has a power of 1. So that means that at this 0, the graph is going to touch it and then turn around. So it's either going to go like this. So at 2, it's going to either look like this, or it's going to look like this, depending on how the graph looks, the rest of it. Multiplicity of 3 means that the graph is going to cross, and actually this one specifically means it's going to cross with a saddle point. So 1, 2, 3. It's going to look either like this, or it's going to look the other way, which is like this. Once again, it depends on how the rest of the graph looks like. A multiplicity of 1 means it's just going to cross the x-axis at 4. Okay, we have the end behavior. We have an idea of what it looks like at each 0. Let's go ahead and sketch a graph. Let's see, we need 1, 2, -3. 1, 2, 3, 4. All right, it goes up to the left and up to the right. Okay, we know it's gonna turn around at the multiplicity. Sorry, multiplicity of 3 is the first one. It's gonna cross it. It's gonna look like this. And then multiplicity of 2 means that it's gonna turn around at this other one. Multiplicity of 4 means it's going to cross that one with a straight line. So this is right here. This one's right here. And of course, the 4 is just a normal 0 right there. So it looks something like that. It follows the end behavior. It looks something like that. Let's go ahead and graph these to show you that I'm just making this up. All right, for the first one, here's the graph. Let me adjust the x-axis. A little bit more noticeable what it looks like. And you can see we have a 0 at -7, -2, and 2, which is what we found here. -7, -2, and 2. Looks something like this. Yeah, it looks something like that. So there you go. And this one, let me adjust the x-intercept again. Okay, and there we go. I had to play around with the intercepts. This was a very low, the function goes very, very far down. So actually goes down to, yeah, -3100. So I just wanted to play around with the y-axis a little bit so that I can get a decent looking graph. And this looks pretty similar to my graph there. It's not exact, of course, but that's because I just sketched it. But that's the basic idea. It just had this weird saddle point here at -3, comes down, comes up at the 2, it turns around at that point, and then it just crosses at the next one. Okay, give it a try in number 3. So these zeros are actually very important for polynomial functions. And so finding them is always what key thing that we want to do, but it can sometimes be difficult finding them. One strategy you can use is using this intermediate value theorem. And this is actually quite an obvious idea, but even the obvious things need to be proven in mathematics, and that's why this comes into play. This actually has a lot more richer meaning when you get into further things, further fields in mathematics, like topology, for instance. But the basic idea is that if you have a value, if a function is evaluated below the x-axis, and then it's evaluated somewhere above the x-axis, and the function is continuous, meaning it never jumps, then that means at some point, so I can just dodge the x-axis at some point I have to cross the x-axis to meet the other point. And at that point there means that there is a 0 between these 2 points on the domain. That's all the intermediate value theorem really states, is that if you have a positive and a negative value, it's a continuous function. You must cross the x-axis between those 2 points. So for this function, we've already factored this thing down. This thing factors down into x plus 2, x minus 2, and x plus 7. That was the function given above that I had sketched a graph of. And we know that it has zeros at -2, -7, and +2. So what I can do is I can take a table of values that evaluate this function out. And that's what I have here, is a table of values. So if x is -8, then f of x is going to be, this is just x cubed plus 7x squared minus 4x minus 28. So -x, all you have to do is just plug it in. So we get -x cubed plus 7 -x squared, sorry, -8x squared, -8 squared, -4 times -8, minus 28. Okay, calculating this, I get -60. For the next one, calculating this one, I get 32. And you can notice right here, we have a jump from a positive or from a negative value to a positive value, which means we know by the intermediate value theorem that there has to be a 0 between -8 and -6. Of course, we already know there's a 0 between those. That's -7. I'm just showing you that it does in fact work. Okay, for the next one, plug in -3. Plugging that in, I get 20. And I can see here that we have a positive value and another positive value. And so the intermediate value theorem doesn't tell us anything about this case. It has to be negative to positive or positive to negative for the intermediate value theorem to come into play. And so there's nothing that we can state about this that says there's a 0 between there. In fact, there is no 0 between there. But even if there was, we could not find it using the intermediate value theorem unless we went smaller interval than this jump of 3 units. Okay, plugging in the next one, I get -18. So by the intermediate value theorem, we know there has to be a 0 between -3 and 1. And of course there is, it's -2. Okay, plugging in the last one, I get 50. And so once again, by the intermediate value theorem, there has to be a 0 between -1 and 3. And there is, it's 2. Of course, in practice, you would never write this thing out. You use a table of values. Desmos will allow you to create a table of values of a function, but you can also have it on a graphing calculator that shows you a list of values so that you don't have to do it by hand, because this is tedious and kind of pointless when you can just graph the function. But this does help you locate zeros in case you can't find them on the graph, or you need to have an idea of what range of values between things, but between which x values will a 0 show up. Okay, give it a try in number 4.